I'm very happy to be here. The CERM is a great place, and it's wonderful to celebrate the birthday of Claude. As most of you know, Claude likes hiking outdoors, and I organized my talk into 5 mountain climbs. Every mountain we climb in about 5 minutes, which gives 25 minutes. So here we go. This is the map that we have to climb today. Here you see the methods I want to explain. Here you see the ages, 1800 to 2000. We'll start with Gauss, climb up stationary iterative methods, then fall back to Richardson's, climb up extrapolation, fall back to Krylov and go to Krylov methods, then domain decomposition and multigrid. And it's organized in a scenery, so as we climb, we will see things. So I start with the green part, stationary methods, and I start with Gauss. Gauss at that time had a very boring life. He was measuring angles during the whole day, outdoors to make maps of areas. So he was outdoors, he measured angles. And one evening he wrote a letter to his friend Gerling when he was measuring during the whole day locations of Bergerwarte, Johannisburg, Taufstein, and Milseburg. And he explained to him what he's doing in the evening. So he says in the evening he's solving linear systems. Here is an example. And these are the equations he has to solve to actually construct the maps. And you see it's a linear system of equations. The unknowns are A, B, C, and D. The right-hand side is on the right-hand side, but the system is also on the right-hand side. And then he says that he is going to now indirect zu eliminieren. Because before he had invented Gaussian elimination to solve such systems. But now he tells his friend he's going to do something else. He wants to use an indirect method. And then he says, bemerke ich, dass wenn 3 der Größen a, b, c, d gleich 0 gesetzt werden, die 4. den größten Wert bekommt, wenn d dafür gewählt wird. So he wants to set 3 of the quantities to 0, and he wants to choose the 4th one, which he does not set to 0, such that when he solves the corresponding equation, he gets the biggest contribution. And in this case, it's d, he says. So he sets a, b, and c to 0. So this becomes an equation for d. You just have to divide the right-hand side by 110. Then you find d. And you don't even have to do this calculation accurately. So he says d becomes minus 201. So he doesn't calculate exactly. It's just an approximation. Good enough. And then with this d, he introduces the d into this column, which changes the right-hand side. So he gets a new right-hand side. Die absoluten Teile werden dann. A new right-hand side. The rest remains the same, and he continues the process. He chooses again the value which gives the biggest contribution, and he iterates. So he's very happy about this method, and he even recommends this to his friend. So he says, fast jeden Abend mache ich eine neue Auflage des Tableaus, wo immer leicht nachzuhelfen ist. Bei der Einförmigkeit des Messungsgeschäfts gibt es immer eine angenehme Unterhaltung. Man sieht dann auch immer gleich, ob etwas Zweifelhaftes eingeschlichen ist, was noch wünschenswert bleibt, etc. Ich empfehle Ihnen diesen Modus zur Nachahmung. Schwerlich werden Sie je wieder direkt eliminieren. Wenigstens nicht, wenn Sie mehr als 2 Unbekannte haben. Das indirekte Verfahren lässt sich halb im Schlafe ausführen oder man kann während desselben an andere Dinge denken. So you see, what he does in the evening... Here I go. What he says is, what I do in the evening after this boring day, I have a relaxing thing to do. I do these calculations. There was no TV at that time. So he says, I do these calculations, and it's very relaxing. You can do them half asleep, or you can think of other things. It's so nice to do this after the boring day of measuring angles. And he recommends his friend to do the same. And he says, never ever he's going to use Gaussian elimination again, at least not if there are 2 or more unknowns in the linear system of equations. So that's Gauss's invention, but it's just a letter. There's no paper, there's nothing. And so there was a real paper by Jacobi, much later, and he actually describes the method. Systematically, a linear system, an iterative process, very nicely described. And much later there is Seidel, who was a calculator of Jacobi. Jacobi in his paper thanked Seidel very much for his very well done calculations he did for him. He was a student of Jacobi. And then Seidel describes the method that Gauss had in his letter, complete description of the method. That's why it's called Gauss-Seidel now. And in addition, Seidel says there will be never ever the need to develop other iterative methods, because here he has a method with which he can solve iteratively every linear system of equations, because he forms the normal equations if it doesn't work. So basically he considers this area of research to be finished at that time. So we've climbed about halfway on the first mountain, and I want to show you how this method works of Gauss-Seidel. Here is a simulation of a temperature in a room. It's a Poisson equation. You have 0 boundary conditions on 3 sides. On this side, you have a boundary condition which represents a door, which is connected to a heated hallway, so it's a certain temperature. The wall also here has a certain temperature because it's a wall to the hallway, but here it's outside, and outside it's 0, and there is no insulation. So it's a bad house, a bad room. And I put a stove in the middle so you can see it's heating in the middle. And I just let Gauss-Seidel run. And I don't show every variable relaxation, but I do a sweep over all variables and show you, because otherwise it's just too slow. So this is the first approximation. So I've done now a relaxation on each variable, just cyclically. Second iteration, third, fourth, 5, 6, 7. You see, it does work. We've done 10 iterations, but we're very far from the solution. So I'm going to do steps of 10 iterations now. 20, 30, 40, 50, 60, 70. It does work. But we're at 100, and we're still not there. So I do steps of 100 now. 200, 300, 400, 5, 6, 7, 8, 9, 10. It's a very relaxing procedure, but you would calculate forever. So a system like this you cannot really solve with this method. So how does this method look like in modern notation? You have a linear system of equations, the discretization of the Poisson equation, AU equals F. You need a splitting of that matrix into 2 matrices M minus N, and then you do this stationary iteration. MUN plus 1 equals NUN plus F. That's how you write all such stationary iterative methods now. And Jacobi you would obtain if you took the diagonal, Gauss-Seidel would obtain if you took the lower triangular. These methods are well understood. Can we make these iterations faster? There are 2 interesting things I'd like to do on this climb. Jacobi, he mentions in this early paper, man kann aber durch Wiederholung einer leichten Rechnung die Gleichungen in andere umformen, in welchen der erwähnte Übelstand immer weniger hervortritt. He says that it's very easy to do preconditioning on your system. You just transform your system, doing some manipulations, and then the method converges faster and faster. This is the invention of preconditioning. The first place I found where somebody talks about preconditioning, he uses Jacobi rotation to make the diagonal heavier of the system. And afterwards, Jacobi works better. Then there is David Young's thesis. Yes? Repeat. So he does Jacobi rotations first, just. German word Wiederholung means that you redo it. You repeat it. So he does first a few rotations, then he looks, is the diagonal heavy enough? If Jacobi is too slow, he does another set of rotations, and so it becomes more and more diagonally dominant, and then his method gives 1 digit per iteration. So this is really an invention of preconditioning. It's fantastic, very, very early. But then it's David Young's thesis, and this is a very simple idea, and it's very, very powerful. What he does is, instead of just taking the relaxed value from the Gauss-Seidel procedure, he takes a linear combination of what it's now and what it was before. And he does it for each variable after it's calculated. It's just a relaxation, it's nothing else. And now we're on top of the first mountain. I show you how this SOR works on this problem. That's the first iteration. You see the shape has drastically changed because there is this over-relaxation parameter that works now. First iteration, second, third, fourth, fifth. You see, it's just dramatic. It's the same process. It's just over-relaxation on each variable. We're at 10 iterations, 20 iterations, 30 iterations. We have basically the solution. Yes, I calculated it because it has property A, this matrix, so we know the value. Yes, yes. So it's just amazing. This is the summit of the first mountain. This summit here, there is a result of Kahan, which is very nice, which shows where the parameter must lie for having convergence. And for this matrix, it has property A, so one knows the best value. So we go to extrapolation methods. So we fall back to Richardson, and then we will climb a mountain where Claude appears, and a famous scientist, CD, as well. So this is Richardson's paper, which is from 1910. It's an amazing paper. Richardson, in my opinion, when I was a student, I had not a great esteem for him because there were simple things he had. He has this Richardson method, which is stupid. It's just a diagonal, not even a preconditioner. There was Richardson extrapolation, which I thought is quite trivial. You just take linear combinations. But this man was just amazing. In this one paper, he has a historical section where he talks about Runge, Hein, and Runge-Kutta methods. Then he has a complete treatment of finite difference methods with very modern notation. It looks like DG notation. He has time stepping for evolution problems. He studies properties of time stepping. He has Richardson's extrapolation in that paper to reach higher accuracy from lower accuracy. And then he gives wall clock times for the computation and computational cost. Wall clock time means he has boys who calculate, and it takes about n divided by 18 pence per coordinate point to pay, n being the number of digits you want. And the quickest boys average 2,000 relaxations of a discrete Laplacian per week with 3 digits. It's just amazing what's in this paper. It's outstanding. And then he solves, he gives Richardson's iterative method, an iterative method to solve the problem. And note, this alpha depends on n. In textbooks, if you look Richardson's method, there is no n here. It's a stupid alpha here. And there is no preconditioner. It's a really dumb method. But Richardson had an alpha n here. And then he solves a masonry dam problem and gives the solution. It's just amazing. This paper is outstanding, outstanding to read. And then what is this alpha n? He looks at the residual polynomial where the alpha appears. You have the spectrum, the eigenvalue is lambda. And then he says, now it has been found that by judicious choice of alpha 1 to alpha t, the quantity, this residual polynomial quantity, may be made small for all possible values of lambda, eigenvalues. Thus, figure 1 shows this done for a set of 7 alphas. This graph was arrived by trial. He didn't know Chebyshev. Chebyshev was much earlier with Chebyshev polynomials. So he generated an approximate Chebyshev polynomial. You can see it almost equioscillates by trial and error, but it's very small on the spectrum. And then he also chooses the roots at the largest eigenvalue. This is a smoother. This is a very, very good smoother. You see, it's completely flat here in the upper half of the spectrum. It's a groundbreaking thinking. So how does this work? We're climbing. I chose exactly 7 roots, but I took the Chebyshev roots, not the approximate ones from the graph. And now we iterate. This is the first iteration. And now you will see a cycle, because it's 7 roots that we do. Second, third, fourth, fifth, sixth, 7. You see at the 7th step, there is something big happening, because now we cover the entire spectrum. And then I cycle again. 7. You see this interesting shape developing, how this temperature is approximated. 21. 30. You see, not quite good as SOR, but much earlier than SOR. It's 1910. It's an outstanding solver with a lot of good mathematics in it. We get in about 50, 60 iterations. We get to the solution. So the dream of Richardson became true in Jean Gallup's PhD thesis. He had studied John von Neumann's results, and because the Chebyshev polynomials have a 3-term recurrence relation, you don't need to a priori determine how many roots you want to have. You can iteratively have the best Chebyshev polynomial at every iteration. And Jean Gallup managed to do this based on an idea of John von Neumann. So now we have the dream of Richardson by having the best Chebyshev polynomial on the spectrum at each iteration. It's still an iterative method, not stationary. And you see, this really works well. It's going a bit too fast. So the disadvantage of this is you need to know the spectrum of the matrix. Otherwise, you cannot generate the Chebyshev polynomial that goes with the spectrum. So there was groundbreaking work by Claude in 1977. There's a fantastic book, Accélération de la convergence en analyse numérique, by Springer Verlag. There are lots of good ideas. A lot of work by Wynne is worked out there in detail. There is contributions by Avram Sidi and collaborators on extrapolation methods. And these methods, they're fascinating because they don't need to know the iterative process. They just need to know the vector sequence. They can generate the vector sequence by linear iteration, all the stationary methods we've seen before, but it can also be a nonlinear process that generates these vectors, and these methods accelerate these sequences to converge faster. The simple ideas are the classical epsilon algorithm, Aitken's scheme. They're on scalar, but they're methods on vectors that work really on vectors, not on the components of the vectors, but the entire vector. So I'd like to show you minimal polynomial extrapolation is one of these methods on that problem. So we're climbing to the top of the second mountain. This is the first iteration. And now, I don't know how good you can capture a movie, but try to remember this movie. This is modified polynomial extrapolation. You see, it looks like the Chebyshev. You also see the little tip. It looks even a little better than Chebyshev. 30 iterations, we are at the solution. So we climbed the third mountain. Now it's the Krylov mountain. We would, in principle, fall back to Krylov, but Krylov did not really solve linear systems in that paper that I looked at carefully. These were eigenvalue problems for oscillatory systems, but the Krylov space appears in that paper. So we'll start with the next people, Stiefel, Rosser, in a conference at UCLA in the National Bureau of Standards. They gave a talk. Stiefel gave a talk, Rosser gave a talk, and they realized they described the same method. They had both invented the same method. It was just unbelievable. So Stiefel went back home. Rosser went back to Hennenfent, his supervisor, and said, there is this guy from Europe who has the same method that we have. Stiefel was from Zurich, and Rosser and Hennenfent were in the US. And so Hennenfent had written a short paper, Iterative Methods for Solving Linear Equations, already in '51. And Stiefel had written a German paper in 1952 über einige Methoden der Relaxationsrechnung. And then Hennenfent and Stiefel wrote this famous conjugate gradient paper together. Now, if you read this paper, this is a paper which is not made for you to understand how they found the method. It's a theorem proof, theorem proof, theorem proof paper. All the properties are there. You have no clue where it's coming from. If you read Stiefel's paper, it's a marvelous paper. It's a 50-page paper which describes how he found conjugate gradients. It's a marvelous way. It's geometric. You see steepest descent. You see how he saw the A conjugate directions that you have to search once, only each direction. It's just fantastically done. There is much more in this paper of Stiefel. There is domain decomposition. He calls it Scheibenrelaxation. There are ideas of multigrid. It's a fantastic paper to read. And amazingly, a third person also invented the same method, Lanchos, also 1952. It's just amazing. So I show you again at top of the mountain how this method works for our room temperature problem. And now look carefully at these iterations. See the little tip coming. We go to 30. They're identical to the modified polynomial extrapolation. It's mathematically the same method. There's a theorem that says conjugate gradients performed on this symmetric positive definite problem is the same as using modified polynomial extrapolation from a basic iteration, which is Richardson, without varying parameter, just a stupid constant, anything you want. It's a fantastic result, fantastic result. And there are more results that relate Krylov methods to these extrapolation methods. So we go to the fourth mountain, the domain decomposition mountain. This is an area where I have done a lot of work. It's very close to my heart. I'm only going to show a small piece of this. It starts with Schwarz. We go way back to 1869. Then there would be contribution of Picard and Lindelöf. These lower parts are not really interested in solving problems, but proving theorems, existence and uniqueness theorems. And then there's Przemyrecki, who was the first to actually use these methods to construct airplanes. And there is a lot of contributions by Björstad, Widlund, Ria Widlund, Ulga, Glowinski, Letalek, Vidrascu, which I will not be able to describe in detail, but I will just focus on the Schwarz method here. And the Schwarz method, the oldest domain decomposition method from 1869, where he tried to fix a glitch in the proof of Riemann's PhD thesis at the end on the Riemann mapping theorem. And the supervisor of Riemann was Gauss. And Gauss never made compliments. We learned yesterday that he was also hiding his ideas. He didn't want to show how he found things. He was actually not a very nice man. I learned from Gerhard Wanner, who learned it from other people. But he gave praise to Riemann in his thesis. There is one sentence in the thesis report that says that Riemann's derivations are partially even elegant. But nevertheless, most of the readers would wish that he had given more clarity and stuff. But this is partially even elegant. Handwriting in Gauss, it's just amazing. So what's the glitch in Riemann's PhD thesis? in the proof of the Riemann mapping theorem at the end of the thesis, you can download it. It's a typeset version, a translated version. It's about 50 pages, 43 pages long on the internet. He gives us an application of his invention of the theory of analytic functions, the Riemann mapping theorem, with a constructive proof, which says that you can map every domain into the unit disk with an analytic function. And it's constructive, the proof. He constructs that function. And to construct the function, he needs the existence and uniqueness of solution of the Laplace equation on an arbitrary domain. And he just says, we take that solution. And immediately he was challenged afterwards. And then he said, but I learned this in my analysis course. Dirichlet showed us the Dirichlet principle. And then Weierstrass gave a counterexample. And then Riemann didn't know what to say. And then he just said, nevertheless, my theorems are true. And there was no proof. And that's what Schwarz tried to prove. He tried to close this gap. Now what he did is he took a domain which has a very special shape. You see it's neither a disk nor a rectangle, but it's a combination of those two, because at that time, the existence and uniqueness of solutions on disks and rectangles to Laplace's equation was known by Fourier analysis and by the Poisson integration formula. So Schwarz knows that on the disk there are solutions, on the rectangle there are solutions, but on the combination, this minimizing Dirichlet principle had no proof. So he invented his alternating Schwarz method. You cut this domain into two pieces. One is a disk, one is a rectangle, and you iterate. You solve on the disk the Laplace equation. Along the boundary where you know what the boundary condition is, you pose G. And along the red boundary, you just pose whatever you think the solution might be, 0, for example. You get a solution on the disk. Then you trace that solution along the remaining boundary of the rectangle, the red part, and you solve. You know immediately by Fourier analysis there is a solution. And then you iterate. You go back and forth, back and forth, back and forth. That's the Schwarz alternating method. And he proved convergence in 1869 using the maximum principle. So he closed the gap in the Riemann mapping theorem proof with this. Because he said afterwards you can add another disk, you add another rectangle for any domain that you can possibly think of. This equation has a unique solution. So we arrive at the top of the second last mountain. I show you the Schwarz method in this example. 2 subdomains only. They overlap here in the middle. An overlap of 4 grid cells. This is the first solution on the first subdomain. Then we do a solution on the second subdomain, first subdomain, second subdomain, first, second, first, second. You see, convergence is very, very fast. These are really PDE solvers. These are made to solve PDEs. Convergence is extremely fast. You can partition it to many subdomains. You need core spaces. But these are very, very good methods for PDEs. Now we get to the last mountain. This is the multigrid mountain. So we fall a little bit back, much less than we fallen back before. So there's just a little climb to do. Fedorenko, who's in there was Bakalov as well, who I did not put on this slide. Then there is Brandt and Hack-Busch, who don't like each other really. If you look at the original papers, they think differently. Brandt is a visionary. He sees how method works. He has a very good intuition. Hack-Busch, he proves things very carefully, nitty-gritty. And there are unfriendly comments already in the writing mutually, so it's not so nice to see. But what's the idea of multigrid? I start again the Gauss-Seidel method. It's the slowest method we've seen so far. But I do it on a coarse grid. So this is the first approximation. You see, it's much better than that flat thing we had before. Just one iteration, coarse grid, very few operations. You see, it actually converges quite well. After 10 iterations, we have the solution. We don't have a fine solution, but it's a very effective method when the grid is not fine. So the idea of multigrid is very simple. To solve such a linear system, you have 2 components that you use. You first use a smoother, which I call S here. You do some smoothing iterations to the Gauss-Seidel, Jacobi with a damping parameter. Then you do a coarse grid correction, so you calculate the residual, you restrict it to the coarse grid, you have a coarse problem you solve, you prolongate to the fine grid, you add the correction, and you do again some smoothing steps. The smoother, as I mentioned, can be one of the classical slow methods. It must be a smoother. Could also be the Richardson method with the 0 put on the high frequency. Prolongation is usually done by interpolation. Restriction is the transpose. The coarse matrix you can even choose without discretization, just a Galerkin formula. And then you apply the idea recursively. So you don't solve the coarse problem either. You just apply the same algorithm again, and you get a V cycle. So how does this work on top of the last mountain? This is the first multigrid iteration on that scheme. Just classical Jacobi damping 2/3. Second iteration, third, fourth, fifth iteration. You see, these are methods that are really made for these PDEs. They're very, very fast. These are the best methods we have. The only thing I did not say yet, nevertheless, you should never use these methods like this. These are stationary iterations. They have a very dumb residual polynomial. It's just the iteration matrix to the power n. You would never want that polynomial. You always want the polynomial acceleration. So you always use a Krylov method. You use these methods as a preconditioner, and then you get the best method. So you need a combination of the mountain 3, which is polynomial acceleration, or the mountain 2, which was extrapolation, with a fast iteration, which has already a very, very good contraction. That gives the best methods. So I conclude with 2 references. This mountain story was actually, over the last years, the motivation to write this textbook. The textbook on iterative methods and preconditions for systems of linear equations. It's built in the same structure as this talk. It has more historic information where the methods are coming from. It has complete convergence analysis for all the methods. Complete, but simple, so you don't need to prepare. You can lecture directly. Every argument is given, it's self-contained. It has small MATLAB codes. You can run and produce such examples for your room or your situation. And it's not too long. I planned about 160 pages. Now it's almost 300 because we have an extra section on optimal control. If you want to learn about optimal control in a simple setting, Laplace's equation is also a good way with iterative methods, which link now this knowledge of iterative methods to optimal control, where the community was not really linked to it. The book that is just appearing in Siam. The extrapolation ideas I liked so much that here in this book, which appeared earlier, the whole Krylov introduction is made through extrapolation methods. I like this very much. It's another view. Here we do it through Stiefel's idea. Here it's done through extrapolation of vector sequences. So it's complementary, and there is much more other stuff in this book. And we also write a review paper now with Gerhard Wanner and Philippe Henry, which follows this same structure with historical content. So thank you very much.
Thank you very much. Are there comments or questions?
Daniel, yes.
I was also consider choosing some of the equations randomly.
Yeah, I repeat the question. So did Gauss also look at random choices, or did he always choose the one that contributes most? In his letter, he always chooses the one that contributes most. And Jacobi, when he introduced the Jacobi rotations to calculate eigenvalues in his paper, he also says you should always choose the equations that give the most benefit. And I recalculated his example with the 7 planets, and at step 6, he actually chose the one that only gives the second best improvement. I don't know why. Maybe it was easier to calculate. He must have had a reason. But in the text, he says choose the one that gives the most benefit, like Gauss. The cyclic one was introduced by Seidel. He just cycles through.
Further comments or questions? And from the people remote, in video? So it's good, there is no further questions, so thank you very much, Martin.
Thank you.